Hi everyone. In this example, we're going to go through a whole list of equations and we're going to interpret what they mean in the context of this problem. So the situation we're working on is that Beth has a garden. She's purchased ladybugs to release into the garden because ladybugs eat aphids and she's trying to cut back on her aphid problem. So L represents number of ladybugs, A represents number of aphids, T represents the time in months since the ladybugs were released. So I just want to walk through each one of these and describe exactly what is happening in the garden according to that equation. So our first equation is linear and it has a slope of 25 and the y value of my y-intercept is 30. So this is telling me that I'm starting at 30 when t equals 0 and then I'm increasing by 25 every time t increases by 1. So in terms of ladybugs, this means that she released 30 ladybugs. And then every month there are 25 additional ladybugs. So if that's breeding or them moving in, whatever, but it's increasing by 25 a month. So here's a pretty version of it. 30 released and 25 additional per month. Okay, formula number 2 is about aphids, not ladybugs. That's an A of t. And we have this 220 times 1/2 to the t. So that 220 is our starting amount. In exponential equations, that a value out in front is your starting amount, your y-intercept. So we're starting with 220 aphids. And then our decay factor, because this is less than 1, we're going to get decay, it's going to shrink, is 1/2. So the number of aphids is getting cut in half every month in this situation. So starting with 220, the number of aphids is cut in half each month. All right, next equation, we're back to ladybugs. This time it's exponential, not linear. This is multiplication, not addition, and the t is in the exponent. So I see a starting amount of 25, and then I'm multiplying by 1.5, so that's exponential growth. The way I would interpret that is multiplying by 1 would mean 100% of what you had. The 0.5 is an additional 50%, so that says the population is increasing by 50% every month. We get half as many added on every month. So 25 ladybugs released and a population increase of 50% every month. So what you'll see is if you want to do percent increase, you're going to have that starting amount times 1 plus whatever that percentage rate is that you're increasing by to the t or the x, whatever we're doing. And if you want exponential decay, you want to decrease by a percent, you'll do 1 minus whatever that percent is. Okay, next one, 360 minus 20t for our aphids. So this is linear, which means we're adding or subtracting by the same amount, not multiplying or dividing by the same amount. This time we're starting at 360, that's our b value, even if we write in the other order. And then our slope is -20. So every month, the number of aphids decreases by 20. So starting with 360 and decreasing by 20 aphids per month. So you're seeing that, notice, a 50% every month or cut in half every month versus increase by 25 ladybugs or decrease by 20 aphids. If it's a fixed amount of ladybugs or aphids, that's a linear relationship. That should sound a lot like your slope interpretations from earlier in the quarter. Next one, back to ladybugs. We've got 60 times 1.12 to the 2t. So here we're starting with 60 ladybugs and then it's definitely increasing because we're multiplying by something bigger than 1, which will make our number of ladybugs bigger. Remember this, if you're increasing by a percent, it's 1 plus whatever the rate is. So the 1 says we have all of what we started with. That's the 100% of the 60 we started with. The 0.12 is an additional 12%. So this one is increasing by 12%. But notice as well that the exponent is different. It's not just a t. Just a t would mean we do it every month. Now, if we plug in 1 for t to see what's happening after 1 month, we've already multiplied by 1.12 twice. So this is actually increasing by 12% twice a month. I would say this little exponent bit is actually the trickiest thing for people. They get really mixed up between 2 times t and t divided by 2. Which one makes it happen faster and which one makes it happen slower. So there's a few ways to think about that. One is you can do the 1 month or 1 hour, whatever your time unit is, you can do the 1 test. So I plugged in 1 for it's been 1 month and found out that it's already happened twice because that gives me a second power. I've multiplied by 1.12 2 times. Another way you can think about this is by thinking about the fact that if you do 2 times t, it's happening twice as fast. So instead of once a month, it's twice a month. Another way to think about it is with transformations, which we'll get to for exponential functions shortly, but that's affecting our input, our x, which is t in this case. So if we multiply our input by 2, that actually does a horizontal compression, so it's going to squash the whole graph in, and we're going to hit our y values twice as quickly. So there's a few different ways, but it's definitely tricky. Think carefully about that one. Okay, last one, aphids. So we have an exponential model. We're starting with 850 aphids. That's our y-intercept. So that happens when t equals 0. Now we're multiplying by 0.6. So this to me means that the aphid population is decreasing, which has been the case in all of these examples. And if we think back to our percent increase decrease, whenever we have decimals, this is a good way to think about it. This is 1 minus our rate, or another way to say it is we're ending up with 60% of what we started with. So the number of aphids is decreasing by 40%. And then once again, we have something interesting happening in the exponent. If it was just a t, that would be every month, but it's t divided by 3. So now if we try the 1 month test, when we plug in 1 month, we haven't even dropped by 40% yet. That's raised to a 1/3 power. We have to go all the way to t equals 3 months before we'll hit the 40% decrease. When t equals 3, we get 0.6 to the 1. So it means we've finally gotten the 40% decrease. So initially 850 aphids, but that's dropping by 40%, which means there's 60% of the original amount remaining, and that's why we see a 0.6 in our equation. But this is not happening every month. We're dividing by 3, which is slowing it down, so it's now happening once every 3 months. So hopefully that helps. We'll work on going the other direction next, but start to think about what all the pieces of these formulas are telling you.